Welcome back to another episode of AI Research Today, the fourth installment of the series. So hope everyone had a nice Christmas holiday break. Is ready to get back into it prior to New Year's 2026. Hopefully we'll see some interesting research popping up soon on the horizon. The paper I wanted to cover today is called DeepSearch, Overcome the Bottleneck of Reinforcement Learning with Verifiable Rewards via Monte Carlo Tree Search. So this is a paper out of Stanford, Uni Tokyo, Washington, Berkeley, AWS, I assume, sponsored some of the compute budget. And I found it particularly interesting because Monte Carlo Tree Search has yet to find its way into many generative AI applications. So if anyone recalls the AlphaGo algorithm, or there's a documentary actually on Netflix called AlphaGo. Very good. Recommend watching it if you get a chance. But it was sort of a combination of PPO, supervised learning, and Monte Carlo Tree Search that allowed AlphaGo to function correctly and solve, or I guess beat the best human player at the game of Go, which until that point had been intractable by computers just because the state space of the Go game is incredibly large, so very difficult to solve with traditional tree searches and RL approaches. So anyways, this paper here, DeepSearch, leverages Monte Carlo Tree Search to help expand the training cycle of an LLM to improve performance on verifiable tasks. So I'll just talk through the paper a bit. So the authors start out by noting that a lot of RL work has seen diminishing returns with prolonged training cycles. So seeing plateaus after a lot of steps with diminishing returns for allocating more computation to additional training depth. So if you're using, for example, a PPO algorithm, generating rollouts, updating your PPO, you're going to hit some diminishing returns at some point. And they call out, along with some citations, that adding more compute or longer train times doesn't necessarily improve the performance of your model. So their proposal is integration of the Monte Carlo Tree Search algorithm directly into RLVR. So Monte Carlo Tree Search is a fairly simple reinforcement learning algorithm. You can think of it as sort of, if you think of a decision tree, where you start at the top or the root of the tree, the root, they would call it an MCTS, and you traverse the tree making decisions on which node to go to using some upper confidence estimate, which is just sort of like if anyone's seen standard Q-learning, just a base estimator using number of visits and log of the Q value and other things like that of the node or leaf you're at. So a leaf in MCTS would be like you've reached the bottom of the tree and you can kind of continue expanding this, generating new branches from the leaf until you reach some terminal state. The challenge with MCTS is the trees can be extremely large, in which case converging on accurate Q values for these trees can be extremely difficult or computationally expensive. And so it is difficult to practically implement in a lot of almost infinite dimensional state spaces, like in in reasoning chains, for example. There's, infinite different ways you could generate reasoning steps to some math problem or a general problem. And so if you treat each reasoning step as a node in a tree, you're going to have like an extremely sparse reward or Q value. So that's sort of what they implement in this paper is a variant of MCTS. So they're still doing a PPO style update and rollout, but the rollout itself is using MCTS to broaden the training breadth, I guess. And they argue that traditional research has focused on expanding depth of the training, meaning how long am I training this for, versus expanding the width of the search, the breadth of the search, and that traditional rollout techniques where you're just rolling out from the base policy don't explore the possible solution space or characteristics of the base policy, which in this case would be the language model, well enough. And so broadening your horizons during the rollout procedure should or could potentially give you improved performance benefits. So they note that they come up with 3 advances in this paper. So one is expanding the reasoning coverage beyond direct policy rollouts, which would be like this MCTS augmented rollout procedure. Fine-grained credit assignments to intermediate steps. So in a lot of RLVF implementations, your advantage calculation is done using the reward on the final state. So you have some verifier that checks if the answer is correct or not, and that's your reward, like in a GRPO style RL algorithm. You take that as a difference of means of the average reward from each of the rollouts in the batch. And so their point here is that they provide a more fine-grained credit assignment using this MCTS rollout, in that they provide Q values to each node in this decision or MCTS tree. And so it provides a more detailed way to estimate value than simply by looking at the final reward of the rollout. And then they also introduce some intelligent node selection and caching strategies to help reduce the compute budget where possible without sacrificing performance gains. So their innovation here is a global frontier selection algorithm that I'll go into a little bit more. I'm just talking to the introduction here. But this global frontier selection allows them to avoid traversing the entire tree in each iteration of the rollout. They also use some entropy-based guidance for rollout trajectory selection, and they use this adaptive replay buffer, which caches historic solutions to avoid having to recompute things that you've done already. Their claim for the results here is that they outperform traditional RLVR baselines, including Nebotron research, and they achieve state-of-the-art accuracy for 1.5B reasoning models. And they also reduce the compute time, so it reduces by around 4 times the amount of needed compute to get state-of-the-art performance during some RLVF tuning. So pretty cool, impactful paper, interesting results. I'll move now into the next section, which is the actual mathematical structure section. So again, at this point, we've just kind of talked through the introduction. So they introduce MCTS to augment the traditional RLVF post-training procedure in order to expand the breadth of the rollouts and see that, along with some other efficiency proposals, algorithmic efficiency proposals, and this kind of improves overall the performance of their algorithms. Okay, how do we describe this mathematically? So given a problem X and a policy model pi, they want to build a search tree for incremental step-by-step solution exploration. So if you think of a trajectory as your original problem X plus the concatenation of subsequent reasoning steps. So X could be solve the problem Y equals 2 plus 3Y or something. Some kind of simple algebra problem. The next problem solution or reasoning step for a reasoning model could be, okay, let's get all of the Y's on one side of the equation. So there are a lot of different potential reasoning steps that could be generated. And we'll think of these as S. We'll just call it reasoning step S. So a trajectory would be X plus reasoning step 1, S1, plus S2, plus S3, all the way to S end, where S end would be the final result of the rollout itself, or the solution to the initial problem X. And we assign a Q value to each step in this reasoning chain. So each S has a Q, Q of S sub I, let's say. And then we want to extract some trajectories. Remember, we denoted a complete trajectory as T from a search tree. And any trajectory can be correct, complete, or incomplete. We also denote the depth of the node, number of visits to the node, number of children to the node, et cetera, as some variables that we want to keep track of as we're implementing this algorithm. So the expansion step, I guess, is the place we want to start, and I'll add some commentary too as we go through this. I actually did reach out to the authors of this paper for clarification on something which I felt wasn't explained enough in the paper, namely around the solution caching. So we'll come back to that later. But okay, so let's imagine at step I of training our model, we have a reasoning trajectory up to the previous time step. So we have the initial problem X plus S1 through Si minus 1, where I minus 1 is the previous time step. We're on iteration I. And now we want to generate the reasoning step I, S sub I, which is the current time step. So we can do this using our LLM, right? We just take all this concatenated input, put it into the LLM, and get the next reasoning step. They generate in candidate solutions for this next trail. And then I'm trying to think if I want to directly follow the way the paper explains it, because I think they could have done a little bit better job on explaining the usage of global frontier selection as UCB during this expansion phase. So let me I'll follow the paper's layout and delay that for a minute. But okay, so let's just assume we generate n possible next reasoning steps from our current node, and we select one of them to add to the tree. And then we just kind of continue doing this until we reach the end state. And during each iteration, we'll have some new set of terminal nodes, which we can verify correctness of using just a verification checker, again, because this is like a quantitatively verifiable task like math or coding. And then we can partition these terminal nodes, right? So a terminal node, of course, has a complete trajectory leading up to it. And we partition these into correct and incorrect subsets. And they do note that in the situation where there are no correct examples, which could definitely happen if your model starts off in a little bit of a rough space, They use this Shannon entropy to select the best negative example, which they define as the most confident negative example. So the thought process would be, okay, I didn't get any of these trajectories right. I've gotten to the end of my iterations that I want to do on this. I need to have some sample selection for this problem for backpropagation. So let's choose the one the model was most confident in its reasoning for, because it was the most wrong there, right? It was confidently wrong in that case. So we perform that selection using the Shannon entropy. So across all of the episodes for which we've generated trajectories, sorry, not episodes, for all the trajectories we've generated off of this initial problem X, we calculate this quantity H, which it might be a little tricky to explain the exact formula over a podcast, but H basically is a token level sum of the log probs. So for each episode or trajectory, you take the number of, you're taking an average over the length of the trajectory. And then for each step in the trajectory, the trajectory's reasoning trace, so like reasoning step 1, step 2, S1, S2, S3, you kind of move across the reasoning step at a token level, calculating log probs for each generated token, and you take the minimum of the negative of that sum, which is going to give you the most positive estimate for the log probs, like the largest estimate. So this would sort of be like your most confident bad example or wrong example, basically. So you generate siblings. You start at the root, generate n siblings, choose one. We'll talk about how in a little bit. And then sort of like continue iterating through your tree until you've reached terminal state. You can partition this terminal state into a set. And then when you're done generating trajectories from this problem, you can either use the correct ones and incorrect ones, subsets, or you can generate the most confident wrong examples as your train set. So either way, you have some train set coming out of this. So after you get some trajectory for backpropagation, you can update Q values, which are initialized as 0. And the Q values are sort of simplistically set up as the previous iteration's Q value plus some decay term plus the sign of the reward or the value of the reward at the end of the trajectory. So like you have some weighting term, like a decay. So the closer the reasoning step is to the end of the process, the more the final outcome plays a role in its value. And the final outcome itself is just directly the correctness of the solution. So this is like when you're when you're writing out your loss function for this update loop, the final reward is taken into account and the Q value of the terminal state. And then all the upstream reasoning steps have this reward sort of baked into it in a time decayed manner up the chain to the root. So you now have generated these rollouts. You've excuse me, generated these rollouts of this root problem, back propagated Q values up the chain. You have some subset of right and wrong problems. So they then discuss this UCT global frontier selection hybrid approach. So it's, again, honestly, I think it could have been made a little bit more clear here where UCT comes into play during the selection procedure, because they do mention it in the paper. But the UCT is the traditional upper confidence bound for trees algorithm, which is like the average reward. So for a step in the process, the UCT of that step is the average reward per visit. So the Q value divided by the number of times that node has been visited, plus the ratio of the natural log of the number of visits from the parent node and the number of visits to this node, plus some lambda to balance like exploitation or exploration. So again, this is just your standard UCT equation for MCTS. And here in this paper, they use that for local sibling comparison. So the idea is at initial time step, we just use UCT to kind of traverse and expand our our Monte Carlo tree. And at the end of this, we back propagate. We, propagate our Q values back up the tree. And then we go through iteration 2 and on. Now we have some number of leaves that have not been expanded, right? So during the first iteration, we generated a bunch of siblings, and we chose one of them to continue traversing, but all these other siblings were left over. So there's sort of like these unexpanded leaves. And so rather than starting all the way at the top of the tree for the next iteration onward, we want to choose which leaf we start our expansion from. So they do this globally. So they look at all the leaves across their current tree, and they compute a frontier priority score. So this frontier priority score is a combination of 3 terms, one representing the quality, which is proportional to the Q value of the parent of this node. A second term in this equation, this is again just a linear additive equation. So you have 3 terms, 3 weighting coefficients. The first term is the quality potential, which is just the tan H of the Q value of the parent node. You have some uncertainty bonus, which again is using the Shannon entropy, which is going to be related to the log probs of the tokens within the step. So you could, depending on the sign of that coefficient, weight it to being more certain or less certain as your priority. And then also a depth bonus, which is just a ratio through the tree, like the depth of this node versus the depth of the overall tree itself. So you compute each of these terms. There's some weighting factor, which are going to become hyperparameters. And then you make a selection of a node that you're going to start from, expanding from. And once you've chosen that node, then you use UCT to traverse the tree, expand the leaves from that node, generate siblings, etc. This has some benefits in that you don't get myopically trapped into what UCT thinks is a good option. You're kind of keeping a global view of the tree. It also reduces the amount of compute needed, so you don't need to traverse the entire tree in each iteration. So a couple of benefits here, and also gives you a way to sort of steer the algorithm using, how important you want to weight parent performance and uncertainty and depth of the node, etc. So that's sort of the rollout procedure. So now we've covered the first couple of sections of the paper. So now at this point, we've talked through how MCTS is used during the rollout generation to sort of traverse this tree. And now we get to the portion of the algorithm which is going to require us to actually perform an update on the policy. So how do we do that? Okay, so They have a couple of proposals here. So when we first start out, and they're using this math data set with, I think, 100,000 problems, math problems of varying difficulty in it. And so they construct the initial subset by looking at the pass rate at 4 attempts from the base model. So iteration 0, we're just constructing the set we want to start training on. And we look at they call it D-hard, data set hard. So they look at the complete training data set. They loop through each problem, generate 4 solutions for the problem. And then, the number of correct solutions is like your pass at K rate. And they have some thresholds that they filter that by. And that's like your initial training data set. And then after each training phase, after each policy update, you rerun the policy on the current training data set, which is, again, a subset of the initial, and filter out ones where it's now succeeding regularly. And they mentioned they set a success threshold of 25%. And this kind of concentrates computational resources on problems the model is struggling with. Now, you might say to yourself, okay, well, what about catastrophic forgetting in this case? Because now we're kind of discarding problems that we've solved and working on ones we haven't. So they use this adaptive replay buffer to get at that problem. So they maintain a buffer population of solutions that were obtained through which they were able to obtain a correct rollout with MCTS, but they still fail the filtering threshold. So at each iteration, we have some subset of rollout candidates. We have some that have correct MCTS associated with them, but the model still can't reliably, even though we could generate a successful search tree or Monte Carlo tree, the model still can't reliably generate successful rollouts at some, K pass rate. So we kind of keep these cached, and we cache our solved problems, MCTS problems. So then now in iteration 2, we have a buffer population, which consists of MCTS rollouts, which we've already done. So we don't need to recompute full MCTS when we've already done so. And we have problems that we didn't get any successful rollouts for. And so they use this sort of hybrid strategy where they incorporate a correct trajectory cache. And for each of these correct trajectories, at the next iteration, they generate some number of new rollouts for it using this updated policy. And then for ones that they never had generated correct MCTS for, they do a full MCTS for. So you sort of like generate new rollouts from previously successful MCTS, and that kind of gives you a baseline of like, is my model improving on these ones which are still difficult, but prevent you from needing like a full MCTS rollout. And then where you're still struggling universally, you generate a full MCTS rollout for these problems. So this saves computational resources. It's just going to make it faster because the full MCTS is going to be a computationally expensive exercise. I did email the authors here because the question I had was, okay, so during MCTS rollout, we generate Q values for each node in the reasoning chain. But if we now, in the next iteration, generate direct rollouts, just using the base policy like we do any normal rollout, no MCTS, where do the Q values come from? The Q values are not cached. The authors told me that they recompute Q values and use the reward from the end of the rollout directly and propagate that back up the tree. So they sort of like recompute Q values based on the reward for the rollout. What I don't know is if these are temporally decayed. I assume that they are, but I'm not totally sure. It isn't directly addressed in the paper or the email correspondence I had. So there are probably a couple of ways you could set that up. But either way, you generate these new rollouts based off your cached solution. You generate some Q values for them. Then you do a full MCTS where needed. That gives you a set of Q values as well. And then you have this union of sets for your training updates, which are MCTS rollouts and direct rollouts. Okay. So only 2 explanation sections left here, and then we'll reach the end of the theory portion or setup of the paper. So they do one thing I won't spend too much time talking about, just Q value clipping. So you could have like a situation in long reasoning chains where Q values explode to very large numbers. So they normalize these with a tanh, which maintains order, but keeps the Q values bounded. So that's just kind of like a Q value regularizer they apply. And then lastly, you have your training objective. And in this training objective, you're summing, when you're calculating your loss, you're summing across each step in the reasoning chain. And for each step, you're summing, like I think about it like horizontally and vertically. Like vertically, you're going down the reasoning chain, S1, S2, S3, S4. And then at each S, you're moving horizontally across all the tokens generated in that step. So like S1, token 1, S1, token 2, et cetera, all the way up to token K, or however many tokens there were in that reasoning chain. So here you have the standard like log prob ratio, which is just like your current policy versus the old policy. They use some clipping, just some epsilon high and low value, like you'd see in a standard PPO sort of thing. They note they remove the KL regularization term to allow divergence. And then they have a step level advantage, which is just calculated as the average reward of terminal nodes in the tree subtracted from the Q value of the step we're currently at. So like for each token in the horizontal movement from reasoning step 1, token 1 to token N, we have a uniform advantage for each token in that sum, which is just the advantage or the Q value for the step minus the average reward for the terminal nodes in that problem. And then each is going to be weighted by this log prob ratio. So that's the loss, and then we would just step our policy. So that's sort of the end of the theory and setup. They compare, so they train DeepSearch 1.5b. They compare it to a bunch of other 1.5b models using various other techniques. They do achieve state-of-the-art performance. I'll note that it could be a little cherry picking because the results are so close. Like one of their math scores is 62.95% for their state-of-the-art model, and some other comparable ones are at 62.02%. So like less than a percentage point difference in performance. And there's some hyperparameters you're choosing here, right? So, you could do many runs of this and find the exact perfect hyperparameters that are going to give you this benefit. But nonetheless, I think so I guess the point is really that you can achieve state-of-the-art performance. It's not, eons better than existing state-of-the-art performance, but you can do it with a smaller compute budget. And that this smaller compute budget is mainly due to the way that they're changing the rollouts during the RLVF procedure. So rather than just doing standard direct rollouts on your policy, you're sort of exploring a wider solution space with this augmented MCTS RL approach. They do a few ablations, like comparing different lambdas, comparing different MCTS integration variants. So recommend taking a look at those if you're interested in implementing this algorithm. But that kind of brings us to the end of the paper. I think that this is a really cool step in bringing a wider variety of RL algorithms into AI training. There are a lot of other algorithms, tree search variants, etc., world model RL algorithms that exist that don't really find their way into AI or Gen AI training very much, but have seen success in other areas of RL. So it is exciting to see this application. I think there are probably a lot more ways you could apply this algorithm in other areas of AI training in general. That'll wrap up the talk for today. So appreciate you listening. If you have any questions, if I said anything egregiously wrong, feel free to comment on the podcast itself, or you can email me at aaron@frankensteinai.com. And other than that, I guess I'll talk to you in 2026. So happy New Year. Thanks.